So today we will speak of another one of our old friends. We're almost done. In fact, this is the last bit we'll do that's really a review of 2126 already. So we'll talk about t-tests today. So you know this formula. We've talked about it many times. To get the probability of a given score with a standard model distribution, mean equals 1, standard deviation, mean equals 0, standard deviation, mean equals 1. You plug it into that formula. So to find the probability of a given value variable, if the variable is sort of distributed, turn it into a z-score, and then you look it up. Right? We've done that before. I had a quick example last time. Think about the IQ thing, right? What percentage of people have IQs between 97 and 102, or how the numbers work, 105. And you turn it into a standard distribution, zeros and ones, because frankly, the calculus has all been done, and you have a nice normal distribution. You look it up in a table, it's pretty easy, right? And as interesting as this is, and I realize it's not that interesting, we're not usually dealing with individual scores, right? Those sort of made-up questions for intro stats, homework assignments of things like how many people have an IQ between 95 and 107, no one asks those questions in the real world. Those are uninteresting to us as far as being scientists. So we're not usually dealing with individual values, we're dealing with means. Right? So instead of knowing about the distribution of x, we usually care about the distribution of x bar, the sampling distribution, which is what we talked about last time. We're usually interested in the sampling distribution of the mean. So what is the probability of getting a mean of a certain type, not of an individual score? This isn't a huge leap, and it doesn't change the Z formula as much as you may think it did. It actually doesn't change the formula per se. Okay? What it changes is what goes in the denominator, basically, more than anything. Okay? And this is because of something called the central limit theorem. Given a population with a mean mu and a variance sigma squared, the sampling distribution of the mean will have a mean of mu sub x bar equals mu, and a variance of sigma squared over n. We talked about this the other day. As n increases, the distribution approaches normal, no matter what the shape of the parent population distribution. And you may have heard tell that at 30, it's normal. It's pretty damn close to normal actually when n is like 5. They become almost indistinguishable at 30. But at n equals 5, you basically have a normal distribution of the sampling distribution. So breaking this down a bit, a population with mean mu and a variance sigma squared mu gave the names. The sampling distribution of the mean will have the same mean, so mu sub x bar equals mu, as the score itself does in the population. It has a variance of sigma squared over n. And we talked the other day about the notion here is that if sigma squared is the variance and then n is the number of observations, the more observations we have, the smaller then the variance of the sampling distribution of the mean will get. It's going to get smaller. And as n approaches infinity, obviously the variance would collapse down to nothing. Because you'd be measuring the whole population all the time, you'd always get the same score. You'd get the mean, you'd always get the mean, so it's going to collapse down to nothing. Does that make sense? So all this is telling us is what the variance is of the sampling distribution of the mean, what the mean is, and what the shape is. And when I say all this is telling us, that's telling us a great deal. That's telling us a great deal. We don't have to really know anything. Right? We know what the shape's going to be. We usually can guess what the mean's going to be. And a lot of times, depending on the variable, we may have an idea of what sigma squared is, though that's going to probably be the problem here. That's going to be our bottleneck, if you want to use that word. We may not know what the variance is. There are some things, and IQ is always a great example, because we know what the variance of IQ is, and a lot of other psychometric tests because they've been developed that way. That doesn't look good. That's better. Don't. Cable. All right. Questions so far? So that's the central limit theorem. That's one of those things you should say to yourself over and over again as you fall asleep. Just repeat the central limit theorem. And I mentioned last time that there is math that can prove this, and I don't think showing you the proof would help anybody either. And it doesn't help me either. It doesn't help me teach anything to you. I don't know it off by heart. So who cares? Just accept it. But also, I think it makes some intuitive sense, and we talked last time about how if we were flipping a coin and we sort of did it intuitively and thought, oh yeah, we'll get a normal distribution. The key thing is no matter what the shape of the parent population distribution. The parent population distribution can be uniform. It could be binary, zeros and ones. We still get a normal distribution for the sampling distribution of the mean. It's very cool. And it is something you could literally try on your own. Take a die, roll it 5 times, that's it. And then, what was the average roll for those 5? Record that. Do that again 30 times and plot it. This is, again, if you have some free time. You'll end up with a pretty much normal distribution. And a die is a uniform distribution. Pretty cool. All right. Questions about this? This informs us, this tells us basically what the numerator and the denominator will be if we're talking about means instead of scores. Okay? So that's really a powerful thing. The population distribution shape does not matter. So a lot of times people worry about is the population distribution, is the variable we're interested in, is the population distribution normally distributed? Don't care, doesn't matter. We can still use z-tests on means because we know from the central limit theorem that the sampling distribution of the mean will be normal. It is a property of the universe that it will be normal. It can't not be, assuming you have random sampling, or something akin to random sampling, let's say. The math assumes random sampling, but then you can violate the hell out of that assumption. It's pretty okay to violate that. Okay. So random sampling matters, but not nearly as much as you might think it does. Because you might think to yourself, wait a second, when people in their 4th year do their psych honors theses, how many times do they randomly sample in humans? The answer would be never. But it doesn't matter. What are called Monte Carlo experiments, basically simulations have been done using very non-random, that's a weird way to put it, but non-random sampling methods, and it still shows up to be the normal distribution. So you have to worry about it. It's nothing to be concerned about. Okay. So to find the probability of a given mean, probability of x bar, we use our old friend, the z-score. For he is our friend, or perhaps she, depending on how you think of distributions. All right. So things change, but the formula itself hasn't changed. We've gone from z equals x minus mu over sigma to z equals x bar minus mu over sigma divided by the square root of n. That's all we've done here. There's nothing magical. And remember, when you learned 2126, you probably thought of these as two separate formulas. They really aren't. It's just a Z formula. The difference is now we're dealing with means, not individual scores. And then the standard deviation, it's sigma for an individual score. Well, central limit theorem tells us the standard deviation is going to be sigma over the square root of n, because the variance is sigma squared over n. Take the square root of that, you get sigma over root n. Okay? Questions so far? You got questions? Who's got questions? Who's questions? Who are questions? Who are questions? What's next? What do you want? So things you want to know.
Okay, can you just break that down again? Like the changes? I just want to.
Well, they aren't really changes. That's the thing you have to realize. A Z score is just a probability, or is going to give you a probability, to look it up, a probability of a given score are in standard deviation units, right?
Yeah.
Now the thing is, we're not dealing with individual scores anymore, we're now dealing with means.
Right.
Central limit theorem tells us that mu sub x bar, which is what we're interested in, is actually the same as mu. So technically this should be mu sub x bar, but we know that's mu, so we can just leave it.
Okay.
And the standard deviation of the sampling distribution of the mean is going to be sigma over root n, because the variance by the central limit theorem is sigma squared over n. Take the square root of that, you get sigma over n, or root n.
Okay.
Yeah. Questions? Other questions? Yes, please. Finish.
So the first formula there is mainly used by population, the second one.
Well, the first formula is used if you want to find, well, the formula itself is just to tell you how many standard deviation units a score is from a mean. That's all a Z score is. It's standard deviation units from a mean. The thing is, we just sub into that same formula if we want to use means instead of individual scores, which is what we're interested in. So we use the sampling distribution of the mean. We use x bar, a given x bar that we calculated. How far is it from the mean of the sampling distribution of the mean, which is mu sub x bar, which is just mu. CLT tells us that. We get that from the theorem. And then the denominator is the standard deviation. What's the standard deviation of the sampling distribution of the mean? It's sigma over the square root of n, right? So, like I said, oftentimes people will think of these things as being two separate formulas, and they are not. It's all just a Z formula. Or if you live in the States, a Z formula. And a friend once gave me a talk at a conference, and he was talking about Z scores, and people had no idea what he meant. Like, really?
So Dave,
yes.
The first one, for instance, we would be using if I were to compare my IQ score to the population.
Yes.
And then the second one would be if we took all the classes IQ score and created it, found the mean, and then wanted to compare it to the population
Yes, sir.
again.
Yes, sir. That is exactly correct.
So in a sense, in the same situation, would it be essential to do both?
No, because this is the question you're asking, right? So are you asking, and this is what Curtis said, like, are you asking, is Curtis different from the population? And he is on so many levels. But is he different from the population in his IQ? And that's probably, right? And the question is, how different, how many standard deviation units are you different from the population? Is just him. If we were to ask, is this class different? We then have to think of this class being a sample of humans, not just an individual human, or as close again as Kirkland's being human. And still Joe, don't I kid because I love. But so here we're asking: is our class different? Is the average score in our class different? And we know this is also going to be 100, but really it says minus mu. It really is mu sub x bar, but mu sub x bar is mu by the central limit. And then what's the standard deviation? It's sigma over the square root of n, because again, the central limit theorem tells us that. So in this case, there's 18, I think it's 18 people in this class, so it's going to be 15, because that we know what the standard deviation of IQ is. 15 over the square root of 18. Square root of 18 is like, what? 4.6 something? So it's going to be 15 over 4.6 something. So whatever that works out. Okay? Make sense? Okay, I think you guys got this. So again, they aren't two different formulas. They aren't two different formulas. I'm sure you were told that they were, and that's fine, because if I was telling you this in 21-26, you guys would be fine. And the other half of the class would be going, my brain hurts! And then it'd be the end of the whole program, and we wouldn't have anybody. And then everybody dies. And then I lose my job.
Finally.
Right? And really, it's all about, do I lose my job? Really, it all comes down to that. A prof, I once asked a prof, and he said, he used to always say, are there any questions I can answer? And then if nobody asked a question, he would say, are there any questions I can't answer? My hand up. He said, yes. And I said, why do we exist? He said, to give me a job. And I thought, well, that's a pretty good answer. That's a pretty damn good answer. He used to also ask, does anyone here not want to be boiled in oil? Like, just to see if people would be paying attention. Be like 4 of us, out of 250 people in this personality class, and each time we go, well, we don't want to be boiled in oil. Okay. So let's do an example of the thing, which is kind of like what we were talking about. Let's say 25 subjects are given an IQ improvement course. I don't know why you take such a thing. I guess, I don't know. Look, I make these stupid examples up, okay? So someone does this. I don't know. Maybe instead, maybe they've been eating a superfood. I don't know. Which are superfoods? Also, anything that people say is a superfood should have more fat added to it to make it taste good. So it's like my kale recipe. It involves a lot of bacon and chorizo and clams. But, or my liver recipe, which is throw the liver in the garbage over a pizza. So we have 25 subjects given an IQ improvement course, and their IQs tested after this quote course, and then their IQs were a mean of 110. Oh, it's not bad. It's not bad. Now, IQ in the population is a mean of 100 and a standard deviation of 15. We use, again, IQ because we know the standard deviation. That's why it's used as an example, obviously. These things. Okay, so we could just do the pluses and the takeaways. X bar minus mu over sigma divided by root n. So we got 110 minus 100 over 15 divided by 25. Note I chose 25 to make the arithmetic easy. 10 over 15 divided by 5, which is 10 over 3, which is 3.33. Oh my God, it works! Stop the presses. I can improve your IQ. For just $19.99. So it's 3.33, which in fact, yours, if you have a Z table on you, which I'm sure you all do, it doesn't go up that high. It doesn't go past 3 typically. If you did look it up, and I did this with my calculator that has a Z function built in, the probability is less than 0.00043. So the chance of getting, what that says is, the chance of getting a mean of 110 for IQ from 25 people, randomly selected, is 0.00043. It's so vanishingly small, we'll say it doesn't come from that distribution, it comes from somewhere else. We rejected all hypotheses. Right? Okay. Good so far? You've done way too many of these back in the day, right? It might have been last term for some of you, it might have been 2 years ago for some of you, but it was like, you've done too many of these kind of questions. Now there's an issue here, actually another big issue. And that's that we don't typically know sigma for a population. The reason as I keep saying, the reason IQ is always chosen as an example in these kind of questions is because we actually know sigma in the population. That's something we don't tend to know. Well, wait a second. The expected value of S squared is sigma squared, right? Remember, it's an unbiased estimator of sigma squared. Right? That's the thing. That's why you divide by minus 1, the whole thing. We talked about that a week ago, 2 weeks ago. Why don't we just sub S squared in for sigma squared? Well, there is an issue here. Now we're not just dealing with the sampling distribution of the mean, we're going to be dealing with the sampling distribution of the variance. Dude. sampling distributions as far as the eye can see. Well, that's going to be an issue. We're going to have to somehow take that into account. And the sampling distribution of S squared will change depending upon n, won't it? Right? Because as n gets bigger, S squared should get smaller. Look, think of how you calculate S squared. You dividing by n. Yeah. It's going to change depending upon n. I'm not going to go into any detail of the sampling distribution of the variance because it's well beyond the scope of the course, but I think you can see, which is, I know, the least satisfying thing every professor ever says. I'm sorry, that's beyond the scope of this course. Whereas in high school, your teachers just made shit up. Well, in university, we go, I don't know, it's beyond the scope of the course. You don't want to know this. You don't want to know this yet. You want to know about the sampling distribution of variance? Wait till your PhD stats here. Maybe you'll learn about it then. And you'll forget it. Because, you know, like, unless you become me and you teach this crap, I'm sorry, this horribly interesting material, nobody cares. Or become a statistician. Statistics, it's the career for people who think being an accountant's a little too edgy and exciting. So, we have to deal with n somehow. We're going to have to take into account the number of subjects. So we can't use z anymore because we're putting in a statistic. It's not a parameter. Z has parameters in it, right, in the denominator. So we have to come up with something else. So we use this exciting new formula. By new, it came out 108 years ago, but and it was discovered. It's called the T distribution. This was discovered by a guy named Gossett, though he published under the name Student. He worked for the Guinness Brewing Company. It's like a dream job. Work in a beer factory doing stats. It's the greatest thing ever. It's like, if I could get that gig, we'll work for Guinness. And he published this, but he published it under a pseudonym. Basically, Guinness they loved their in-house scientists publishing. They loved it. That was great. Be a scientist. Just don't do it under your name. We don't want you to be hired away by another brewery, basically. We don't want you to be hired away by a different brewery because they're Irish. So I just knew we're Irish guy, right? This next song is not a rebel song. This song is Sunday, Bloody Sunday. So, as Bono. Jiggle. Breathe a lot. Yeah, sorry, I'll stop my Bono impression now. Question.
Kind of unrelated to horse material. Why would a brewery need a statistician?
Oh, think about things like quality control. Right? So you're going to take, you can't, as much as you might want to when you're at the Guinness Brewery, you can't sample every single batch. Right? You can't just sit there and go, well, this beer's good, it's all gone now because we drank it. Can't sell this one, we drank all the beer. So what you're going to do is you would sample, and this, in fact, there's a lot of application for statistics in industrial situations because you're always just sampling things. You can't take whole batches. Same thing with M&Ms. The reason M&Ms are used a lot in statistics examples and probability is because there's these different colors, and it's great. But M&Ms actually have people that sample the batches that come out and see how many reds, how many yellows, how many browns come out. And in fact, Hershey makes M&Ms, right? They actually, when they found out, this is in the 1950s, when people started using M&Ms as examples in stats classes, if you're a stats prof, you can call Hershey's and they'll send you all kinds of data on M&Ms. Yeah, so I mean, it's used industrially all the time. Yeah. It's a good question. I remember thinking and asking a similar question myself, and it's like, oh, yeah, it makes complete sense. Right? And he doesn't know, so Gossett doesn't know. It's like, I don't know what the variance of whatever the hell he's measuring, of how, let's say the alcohol content of the beer. I'm not going to know what it is in the population, but I can get a sample standard deviation easily and calculate that. So you'll often hear it called student's t-test, and he published under the name student. But his name wasn't student, his name was Constance. So you see how similar this is to the Z? We've just taken the sigma out and put an S in. That's all it is. So remember, T changes depending upon the number of observations because of the sampling distribution of the variance. Care about. Basically, when you work this whole thing out, it changes depending upon the degrees of freedom used to estimate sigma squared by calculating S squared, to be more precise. The other way to look at it is how many things did you have to calculate, did you have to fix to calculate the variance? And to calculate the variance, you need to calculate the mean. So you need to fix one quantity. The other numbers can't vary. Remember, the last one does because they have to add up to a certain amount. Right? This is really cool because now you don't have to know anything. You have to know anything with the population.
Okay, that's the difference though, between Z and T is whether we know the parameters or not.
Well, we don't have to know the variance anymore, which is something we hardly are ever going to know. You can usually come up with some value for mu that you want to see if it's different than. Let's think back. Let's say that they wanted to make sure that Guinness was about 4.5% alcohol, which is about what it is. I think it's 4.2. Doesn't matter. They're looking for, are batches on average significantly different than 4.2? Let's say. So they just set mu at 4.2. That's easy. Now all I have to do is calculate the average, calculate the standard deviation, and I can see by doing a sample of, say, 10 batches of beer.
How often?
Is it vary enough that I care? It's going to vary. Is it enough that I'm going to care about it? Is there something weird going on? Maybe we changed our manufacturing techniques of some sort, or something. We changed the yeast strain, whatever.
I went to write something down and I forgot. Can you say what you said about the degrees of freedom again?
Oh, the degrees of freedom here, basically, it's the degrees of freedom for calculating S squared, and all that is the number of values that are fixed. Right? So it's the number of total observations minus the number of fixed values.
Okay.
One has to be fixed. Remember, when we add all those things up, they have to sum to a certain number to calculate the mean. So that final one is fixed. So we've lost 1 degree of freedom.
And how does that differ from the previous formula?
Which one?
Like the one that we're changing from?
Oh, from Z?
Yeah.
We don't have to worry about that because we don't have to calculate sigma. It's a thing. It exists.
Okay.
Yeah, we don't calculate.
So that's
it.
what changes when you...
Yeah, it's a property of the variable is sigma.
Okay.
Whereas this is a property of something we calculated, so we take that into account.
Okay.
Yeah. So one of the easiest ways to look at this is how many degrees of freedom have you lost? How many means did you have to calculate? We had to calculate one mean to calculate the variance. What if we had pairs of observations? So before and after. Okay.
From the same people, per se?
It could be. Yeah, it makes sense.
Because this one's for related.
So it's pairs of observations. So you paired them up somehow. Usually it's for the same person, or if you want to use technical statistical terms, the same experimental unit. Or it could be you maybe match them somehow.
So it's related, right?
Yeah. So this is this average difference, x bar sub d, divided by the standard deviation of the differences, divided by the square root of the number of pairs. Now, technically, this is again, you often see this as a separate formula. It's called, people call it repeated measures or dependent sample t-test. But actually, it's the same damn formula. And you're thinking, wait, yeah, but there's no minus mu. Yeah, sure there is, but what's mu equal when we expect no difference between two groups? 0. So are we going to put minus 0 on top? Yeah, I guess if you're a pedantic twit, which I am, but not about statistics. Why put minus 0? But technically it's there, so minus the mu and the mu is 0. Right? You expect no difference between the two groups. Or between, not two, it could be two groups, or between before and after. Right? So let's say we were all given, we could do the IQ improvement one, right? So we all measure all our IQs before, then we give Dave's mystery course, and then we measure our IQs again. We would expect, if there's no effect, if we take Mitch's score after and subtract his score before, we should get, well, if there's no effect, 0. Now there's going to be some fluctuation, of course, might go up 1, might go down 1, might go up 2, might go down 2, but on average it should be 0 if there's no effect. So the mu is 0, so why would we put minus 0 up there? And again, that's why you always see this formula, you always see this formula is different. In fact, it's the same damned t formula. It's just, we've got differences here.
So the SD gauge is the standard deviation of differences?
Of the differences, yeah. So you calculate, so you do Mitch before and after, and you Brian before and after, and Kurt before and after, and you do Dave before and after, and you Rachel before and after, and then you take all those numbers and you do the standard deviation of those.
Okay.
Yeah.
You do it of the differences, right?
Yeah, of the differences. And then the n is the number of pairs, the number of. Yeah. The numbers don't know where they came from.
Yeah.
So just because they're pairs of numbers and we subtracted to calculate them, the numbers don't know that.
Okay, so let's say we had 5 people, 2 measurements, and it would be 10.
No, it would be 5.
5,
And then if it was a big n, it would be 10?
No. No, it's because it's before and after, and what we're trying to find out is it different from 0?
Okay.
Right? So the thing we're calculating
Yeah.
is the difference score. And that's the standard deviation of those difference scores.
Okay.
The numbers don't
Yeah.
know that they're different scores. They don't care.
Okay.
The t-distribution doesn't know this.
There's another formula with big N when we're doing multiple groups or something like that.
I wouldn't use big N.
You mean you wouldn't use that as a
Not in this case.
notation?
No. Not in this case. Okay, questions about this? Some of you are you're discussing it, that's fine, but do you have any questions? Like, is there an argument somewhere as to settle?
So it's the mean differences,
Yes.
standard deviation differences,
Yes.
and the number of pairs.
Correct. And that's because, again, we're just trying to find out, is it different from 0? So actually, technically, it's x bar sub d minus mu is 0. Divided by s sub d divided by root n. And why would we put minus 0? Right? And now sometimes you will see, to trick you, in intro stats, homework type assignments will say, we expect the difference to be 5. No one ever does. So then technically it's x bar sub d minus 5 instead of 0. It's always going to be 0. You don't expect it to be anything other than 0. Your null hypothesis is they don't care. Okay? Okay. Any more questions on this? Do you see how it's all the same damn formula so far? Yeah, standard deviation, the differences. Because what you're trying to find out is, are those differences different from 0 on average? That's the question you're asking. So, this can be used for pairs of observations, not just before and after, so we could pair people up somehow. Yeah. So, I don't know, let's say it's a blood pressure medication. And one group gets, one member of the pair gets a placebo, the other group gets the blood pressure medication. And what we've done, we'll say that this is the group here, and we've matched people up on their blood pressure. And it turns out that Keegan and I have exactly the same blood pressure. You poor bastard. So, actually my blood pressure is low. Which is good, because I'm so hyper that, you know. So in that case, we treat the two of us as a pair. And I'll get the placebo, you'll get the drug, and we'll see what the difference is. You can do that. So that's matching, basically. Now remember, the subjects now are different on every other variable except the thing we've matched on. So you have to have a really good reason to do this kind of matching thing, unless it's just before and after stores. All right. What if your pairs aren't matched? What if you just have two groups of scores? Well, maybe you have two populations. That would be the alternative hypothesis. The null is they come from the same population. The hypotheses then are as follows. HO is mu1 equals mu2. Mu2, of course, my favorite band. Thank you. Many people say they're just average, but that's the closest thing to a statistics joke anyone's ever made. And HA, or ha, is that mu1 is not equal to mu2. They're not the same. They are not the same. They're different somehow. How? I don't know. Okay. So how are we going to test that? Well, let's go back to the original T formula, which is that. We have a statistic, x bar. We have an HO value for the parameter, mu. And we have what we call error. It's the standard deviation of whatever we're interested in. Okay. So that's the three things we have. So what we have to do now is figure out what goes into the places for statistic, for the HO parameter, and for the error estimate. Okay? So that's all we have to do. Again, it's all the same damn T formula. We're just trying to figure out what goes in each place. Okay. So, x bar 1 minus x bar 2, or 1 minus x bar 1, doesn't matter where we put it. That's our statistical stuff. Remember what our HO was, mu1 equals mu2. Practically then this becomes, let's worry about the error in a second, x bar 1 minus x bar 2. Technically it's minus mu1 minus mu2, but we know those, our HO says they're the same. So if you get mu1 and mu2 are the same, two things, one thing that's the same as the other thing minus it is 0. So we just leave that out. Technically it's there, but it's got its cloaking device activated. It's Romulan mostly. Star Trek, nobody? Or maybe it's the USS Defiant operating in the Gamma Quadrant. I'm watching a lot of Deep Space Nine lately.
It's not there because it's the same?
Yeah, it's not there because they're the same thing, right? If the null is mu1 minus mu2, or in fact, think of it this way. mu1 equals mu2, right? The other, we can rearrange that and say mu1 minus mu2 equals 0. So really, that thing should be 0 anyway, because our null is that that's 0. So it really comes out to 0. So we just take it out. Yeah, makes sense? Perfect.
So then, if we were to find a T statistic that was not significant, that would mean that mu1 is not equal to mu2?
That would mean we have no evidence that mu1 is different than mu2. If it's not significant, we have no evidence that mu1 is different than mu2.
If
We've had a
it would be the opposite,
they
right?
would say that they don't come from the same distribution, that mu1 is not equal to mu2.
Okay, that's what I meant.
Yes. Okay. Other questions? This is good. You guys are asking good questions.
So it's just refreshing. It's
No, exactly. That's part of why I'm doing this. Yes, guys.
So we always just
Yeah.
Well, yeah, because we always have the null hypothesis parameter is always the thing on the right in the t-test. Just like x bar sub d, technically it's minus 0, but why would we put that there? It's just extra usage of our pen, right? So same thing here. We assume that mu1 and mu2 are equal to 0. In fact, the null does that.
Is there ever a situation where we would assume these are not equal?
Yeah, technically one could, but you would not do that. Like that, practically you would never do it. Technically you can, and this is one of the cases where this comes up as bonus questions in the final hard bonus question in the homework is this. But no, in reality you would not do that, right? When you're using this to apply it. There's nothing mathematically wrong with that, but when you're using a t-test actually as a tool and not as an end in of itself, you would never do such a thing. But yeah, you can. There's nothing wrong with it. It's just that you would not see a research question asked that way. It would be a really weird question to ask. Yeah. Because it'd be a different way to answer it. Right? You just, I don't know right now, but it would be hard for a lot of people when they read it to understand it. Because a lot of people don't remember when they're reading journal articles, and I kid you not, I include, full professor tenured faculty people read statistical things, all they remember is their intro stats. They don't anything else, it's gone. Unless it's like me or Paul when we teach this crap, we care. But you would not believe the amount of stuff when I review articles for journals and I go, yeah, you did this, your results are done wrong! And I send it back to the author and they go, oh my God, I'm sorry, I forgot, and they fix it. Right? So most people don't even remember that. So one could do it, but a journal editor would go, you do that a different way because you're going to confuse everyone. Yeah, it's a good question. Brilliant question.
Okay, so when I'm looking at this formula, I see that where the statistic goes, HO and error.
Yep.
And I understand the HO, but
Yep.
I can't stop thinking about like what if HA was true?
Yeah, we don't ever know that HA is true.
Okay, so
all we're
that's
trying
why-
to do is determine is HO not true.
And that's why HO is in the formula then.
Yes.
Okay, because I keep
I
thinking
almost
the
dropped to my knees
alternative.
and thanked. I saw a little light bulb.
It did, yeah.
Yes.
I just wanted to confirm.
No, that's exactly correct.
But I just kept thinking like what if HA was
We
true?
are always
like-
assuming HO is true.
Right.
And then we're trying to find out. There's an assumption in every statistical test we're going to talk about is that HO is true.
And the margin of error is based on
And that's why.
And then we find out, well, the probability says no, we must have violated an assumption. Oh, you know what assumption we violated? That HO is true! So HO is not true.
Okay, so that's why it's a component of the formula.
Yeah, exactly. Beautiful. I know I got a little excited there. I shouldn't overdo it in this class because I got another one right after.
That's probably the most clearest thing that I've.
No, that's wonderful. No, it's wonderful that you got that. That's beautiful. That's beautiful. It's part of that's sort of my job here. So when things like that happen, it makes me very pleased. With myself, not with you. So
Just a little.
maybe a little. Okay. Now the error is a little bit weirder because I think you can see where the stat part comes in and where the parameter for HO comes in. The error is weird. We have to weight the variances. Because what if they're have two different ends? Right? We have to divide by the number of subjects. So s squared sub 1 divided by n sub 1 plus s squared sub 2 divided by n 2. And you might say, why don't we subtract them? Because you can't. Distributions don't work like that. Just accept that. You're all Catholic and I'm Pope Dave I, okay? It works that way. So we're going to weight them somehow. We may as well weight them by the number of observations. So now our formula is this. Oh, does that seem vaguely familiar? Yeah, that looks just like a freaking t-test for two groups. Except we derived it. X bar sub 2 minus x bar sub 1, or 1 minus 2. Conventionally, what you do is you put the first one, the bigger one first, because you need a positive value. It doesn't really matter. Divided by the square root of the following quantity, s squared sub 1 divided by n1 plus s squared sub 2 divided by n2. So it's the same formula all the time. We've just added different values in for the statistic, for HO, and the error. And again, technically it's x bar sub 2 minus x bar sub 1. minus the quantity mu1 minus mu2, which should be 0, so I'm just leave it X. Just leave it out. Now, this formula assumes something. There's a little something extra. And that's that the two variances for the populations are the same. Meaning that the two standard deviations should be the same. And when I say the same, I mean roughly the same. As a rule, is one twice the size of the other for a t-test? It's more than twice the size? The test gets more conservative. In other words, you're going to get more type 1 errors. You don't want those. You want to avoid type 1 errors if you can. So, if the variances are actually not equal, so to make a test that has a little more power, perhaps, you have to pool the variances. And that's where you get something, you get this thing called the pool variance. It's just a way, it's a weighted, right? Weighted by the degrees of freedom. 2 S's divided by the degrees of freedom. We've lost 2 degrees of freedom here because we've calculated 2 variances. We need to fix 2 means. X bar 1 and X bar 2. We calculated S squared 1 and S squared 2. Okay?
So we pool when the size of the groups are different? Because that's what we were taught last
It's not quite that simple.
So when the variances are not equivalent?
Yeah, but a good rule of thumb is when the size, when the number of observations are quite a bit different. And the question you might ask yourself is how a bit is quite a bit.
Yeah.
Right.
And the answer is, I don't know. You really know that's actually the answer. There's a final way to do this, which I'm not going to show you the math for because it's matrix algebra, but a computer will do it, and it's actually the most accurate way. Yeah, but
Well, because the last formula you said assumed that the two variances for the population are the same.
Yes.
So it's fair to say 99% of the time we're going to assume that?
It's safer to assume this is a safer statistical test.
Okay. So unless given those two values.
Well, if you're giving them and they're almost the same, like you get the same number of observations, and you've also got what, I don't know, how about one's 10.1, one's 9.9, I use the other one.
Yeah.
Because they're basically the same.
Yeah.
Yeah.
Okay.
And the rule of thumb tends to be is one twice the size of the other, and they have roughly the same number of observations.
I think last semester I had a hard time knowing how small
Yeah, when you
the difference.
Yeah. No, and it is, and the part of the problem is because there isn't really a hard and fast rule. There's a lot of rules of thumb.
Right.
Yeah.
But we only
How many degrees of freedom do we have here?
Bless you.
How many degrees of yeah.
you only lose degrees of freedom.
Now, how many degrees of freedom do we have? Not just 2. How could it just be 2? It would always be 2. The formula is that's just 2. No, it would be. Generally, what's the degrees of freedom for this? N1 plus N2 minus 2.
Oh, yes, I know
Yeah.
that.
Okay. There's a final way to do this, which is more accurate, which involves using matrix algebra. So I'm not going to show you to do it by hand because no one does these by hand. But you will find when you do, if you do a t-test with SPSS, okay, it's going to give you a couple of different answers. It's going to tell you variance is equal, variance is not equal. It's going to give you both of those. And then it's going to give you something called partial degrees of freedom, where instead of having N2 plus N1 minus 2, it's going to be like, so let's say that ends up being 18. Remember the degrees of freedom like 17.3. What? Just accept it. That's the one, in fact, it's the most accurate.
Is that matrix thing we're talking
And that involves you doing matrix algebra, we're not gonna get into that.
Okay.
And no one does that by hand anyway. But usually they'll all agree. Usually they'll all agree. Right? Not always, but usually.
How many degrees of freedom?
Yes, please.
How many degrees of freedom were in that? I missed it.
How many degrees of freedom?
We said 2 and you said no.
And, well, no, he's getting 2.
Right, right.
The N1 plus N2 minus 2.
Oh, that's it.
Yes,
Okay.
These two,
in general. N1 plus N2 minus 2.
because they have to be roughly the same. So these two
When you're
are
pulling.
about the same.
Or the other way. You still set 2 degrees, you've still fixed 2 means, so you still have lost 2 degrees of freedom.
Right, but the original would be N minus
So say
1, correct?
this-
Yeah, because you've only
say
fixed
this
one
is
thing.
Right.
equal to
Okay.
50 people.
That makes more sense.
Good. Okay, assumptions for the t distribution to be accurate. Simple random sample. You can violate the crap out of that, no one cares. But the math actually that is behind this, that Gossett discovered, needed a simple random sample, and that's because of the central limit theorem. The central limit theorem wants a simple random sample too, but as I noted before, you can violate this and not care. You have independence of observations. You cannot violate that. The math falls apart when they are independent observations. Independent observations, all that means is if I know Joey's score, that doesn't allow me to predict Richard's score. Okay? I can't predict one score from another. I would take care of that. Typically, we take care of that through research design. Right? You cannot violate this assumption.
When you're dealing with one individual based on one score predicting another, can you make that assumption?
You would never do a t-test on one person. It wouldn't make any sense.
Okay.
You have n of 1. You can't have n of 1 because you'd have 0 degrees of freedom.
Okay.
Right?
Yeah.
When you're doing case studies like that, you don't tend to do differential statistics in general.
Oh,
You
okay.
usually just report this is what happened.
Okay.
You might do like an ABA thing, so you say before, during, after, and then you can look at those kind of things.
Okay.
Yeah. That's why like old operant conditioning papers, things written by Skinner, things like that, there's no statistical analysis in it at all. It's just like, here's the behavior.
Mm-hmm.
Right? Skinner had this wonderful quote that the average describes no error. So he was opposed to using inferential statistics. So, and I don't, he's right, though I also think that this stuff's bad. Homogeneity of variance. Now, this means the variances have to be equalish. Technically, it means they have to be equal. Because when we have our null hypothesis assumption, which is that mu1 equals mu2, it follows from that, if they're the same distribution, that sigma squared sub 1 equals sigma squared sub 2. We can violate this. Not horribly, but we can violate it. We can violate it about double. Is one twice the size of the other? You can even test if the two variances are different. Use that very simple statistical test. You divide one variance by the other. Look it up in an F table, it's not hard to do. The more conservative statistical test involves pooling and assuming the variances are equal. So oftentimes when you get the input from something like SPSS or SAS or whatever, take a look and just look for the one that says variance is unequal. That's going to be the more conservative one. And you want to be more conservative if at all possible in statistics because you don't want to make a fool of yourself. So that's the homogeneity of variance assumption. Questions about this stuff? Good? We have a quiz, or you have a quiz, I don't have one, coming up on Tuesday. And then you have a test on Thursday, but also on Tuesday is probably conceptually the hardest lecture of the whole course. Don't miss that one. And it's on statistical power.
And we'll be tested on that.
That'll be on the test, yeah. And on that note,